Hi, welcome to week 6 of this course, Digital Circuits and Systems. And in week 5, we saw a lot of things, and so there was quite a bit of contents about CMOS VLSI circuits, what the delay of a CMOS circuit is, and so on. And I also believe that the homework that is given in week 5 itself is quite hard. So what I want you to do is take some time to solve the problem so that you understand all the concepts, and anyway the deadline is past the usual deadline. So the deadline is Sunday for homework 5. So I suggest that you take your time and solve the problems and understand all the little concepts, because they will be useful for you, if not in this course, somewhere else later. So in this week what we are going to do is we are going to look at state machines. So we are going to look at finite state machines and how sequential circuits, what are the special class of circuits called state machines, and how to design them, and so on. So it is a very fundamental thing to many digital design courses as well as digital systems itself. So it is important that you pay attention to the details, and I am going to show you a lot of different tricks of the trade, so called tricks of the trade. So I suggest that you follow the material carefully, and the homework assignments that you will see this week will also reflect the kind of problems that are there in the videos. So in the last week we left off with this place where we saw that if I want a sequence to be detected, then we can put in a shift register and we can do a few things about the shift register itself. And however, what would happen is, if the patterns become complex, or if there are many patterns that you have to look for, then the approach that you have using the shift registers will not work, and shift registers also solve only a small class of problem called the detection problem. So we will see several examples now, and then we can go back and think about where the approach that we used in the last class fails. Let's start with a design problem. So before getting into this week's design problem, there is one class of flip flops that I didn't talk about so far. This is called the JK flip flop. So the J and K does not really mean anything, it does not stand for anyone's name, or it does not stand for any particular thing. This is a flip flop that was in use for many decades, but JK flip flop is not something that is commonly used in designs nowadays. So however, it is good to know what the flip flop is. So as any flip flop is, you have either a positive edge triggered or a negative edge triggered flip flop. In this case, let us assume that we have a positive edge triggered flip flop, and the characteristic table is as follows. If both J and K are 0, then the output Q, so the output Q star, or the next state of the flip flop, is the same as the current state. If K is 1 and if J is 0, the output is 0. If J is 1 and K is 0, the output is 1. However, if both are 1, then the output is Q bar. So this is Q bar, I am sorry about that, this should have been Q bar or complement of Q. So this should have been Q bar. Now in summary, we can say that J is equivalent to set, K is equivalent to reset. If both J and K are 0, keep the old value. If J equal to K equal to 1, then toggle the old value. So this is the setup behind a JK flip flop. So this table has to have Q bar here instead of Q, and this is a standard flip flop that you will see in many textbooks. So I just want you to be introduced to it, so that you don't go back after the course and not know what the flip flop is. So what I am going to do in the next few minutes is take this particular circuit here, which is designed using a JK flip flop. So it is a flip flop and it has a common clock connected to it. So it is a synchronous circuit, and to this synchronous circuit there are 2 inputs and 2 outputs. The J and K inputs are there, and Q and Q bar are the outputs of the flip flop. There is a single input called X to this whole circuit itself. The sequential circuit takes X as the input, and the outputs are Q0 and Q1 itself. So let us say this is the circuit, and you are asked to find out the state machine that this circuit describes. So I already described what a state machine is in the previous video. So let us see how to approach this problem of given a circuit, how to analyze the circuit so that you can get a state machine. So this is one part of the problem, how to figure out what somebody else has done. This is something that you may have to do in your work also. There is a circuit that is already given, you are trying to figure out what it is doing. So let us see this circuit. The first thing you have to do is you have the J and K inputs for both the flip flop Q0 and Q1. You can now go and write equations, right. So you can write the input and output logic equations. So if you look at J0, it is Q1 and X complement, then K0 is Q1 and X, J1 is X itself, and K1 is X XNOR Q0 or X XOR Q0 complement, right. So this is these are the inputs. This is something that you can fairly quickly derive based on the circuit itself. If you look at this circuit, right, this resembles the canonical circuit in some sense. You have the state registers which are given by Q1 and Q0, and the input forming logic, so, or the next state logic is here. So based on the current state and the current input, you drive J and K inputs. So these J and K inputs will get based on J and K, Q0 and Q1 will change in the next state. So if you supply current state here, then this logic takes care of forming the next state, and when the clock pulse comes in, the next state gets registered. There is no output forming logic here. Q0 and Q1 are directly given as output. So these are just wires, there is no gates there, there is just wires there. So it is a valid synchronous sequential circuit, and from the canonical model, the only thing that has degenerated here is there is no output logic explicitly, right. And to be more specific, since the output is Q1 Q0 explicitly, it is only the flip flops that are controlling the output. So this is actually a Moore machine. I mentioned this in the last video. This is actually a Moore machine where the output depends only on the states but not on the inputs directly. So this is a Moore machine. Now I want to find out what the state diagram for this is. So once you have the equations, so let us say I have this present state and the inputs. So you have the present states could be 0 0 0 1 1 0 or 1 1, because there are two flip flops, they can be in 4 different combinations, and x equal to 0 and x equal to 1 are two combinations of x. So overall from the input side we have x, q1 and q0. There are 3 inputs, which means there are 8 combinations. So these are 8 combinations, and if you go and look at what the output of the next state logic is, the next state logic actually drives J0, K0, J1, K1 based on Q1, Q0 and X. So based on these 3 inputs you derive J1, K1, J0, K0. So for instance, if I want to derive this column J1, J1 is X itself, so I take the value of X, put it there. K1 happens to be X XNOR Q0, so it is this column vector XORed with this column vector, and that is XNORed with the third column vector, so that is K1. Similarly you can derive J0 and K0. Now that you have J0 and K0 and J1 and K1, you can actually determine what the next state is going to be. So let us look at Q1 star and Q0 star, these are the next states. So if you place J1 K1 J0 K0 before the clock edge arrives, then when the clock edge arrives the J and K values are sampled. So your clock is the triggering signal, J and K values are sampled, and based on the semantic of J and K, whatever the values of J and K are, the flip flop values Q1 and Q0 will change. So let us see how this is going to happen. So let us take the very first one. So J1 is 0 and K1 is 0. So if I look at this combination, K1 is a 1, which means it is a reset. So whatever the value of Q1 is, you do not care about it, you have to reset. And if you look at J0 K0, it is 0 0. So 0 0 is keep the old value. If you go and look at the old value, it is 0 itself. So we have Q1 star is 0 and Q0 star is 0. Let us look at the next row. The next row says J1 K1 is both 0. If both are 0, then keep the old value is 0 itself. So, this is 0, and for J naught and K naught it says keep the value of the flip flop Q naught at the present, whatever the present state is, continue in the same state, right. So, 0 0 will take the present state which is 1 and you get 0 1 here. So, remember I am not doing this as a sequence. So, these are combinational inputs. For each of the combinational inputs for x q1 and q naught, the combinational circuit that drives j and k will drive these values, but when these values are put in as inputs to the jk flip flop, the jk flip flop in the next clock cycle will have this. So, the next clock cycle when I have 0 1 here, for instance, this is just saying that flip flop 1 will have a 0 and flip flop 0 will have a 1. Let us see the next one. So, J1 K1 is 0 1, which means whatever the value of Q1 is, do not care, but go and reset, right. So, 0 1 means K is equivalent for reset. So, reset Q1 flip flop and set Q naught flip flop. So, you have, when you reset Q1 flip flop it is 0, when you set Q naught flip flop it is 1. So, you get the state 0 1. If you continue this way, you can get all the other values of Q1 Q naught. So, that is what you have here so far. So, let us look at this particular row. So, in this particular row, if x is 1, Q1 is 0 and Q naught is 1, J1 K1 are both 1. So, when both are 1, toggle 0, that gives you a 1, and J naught K naught happen to be 0 from the equations. This keeps the old value itself, which is 1. So, that is what it is, and in this circuit there is no output. So, we just leave this as a blank column. Now, what we have is, if we forget the inputs for a while, based on the present state and the input x, you can derive the next state. So, forget the flip flop inputs now, you do not need it anymore to draw the state machine, because you have already derived the vectors q1 star and q naught star. Once you have that, you can forget these 4 columns in the middle. So, based on the input and the present state, you can get the next state, and output we know is just q1 star and q naught star itself, we are not explicitly writing that. So, this is what you want for a state machine. You want, if this is the input, this is the present state, this should be the output, and so on. Let us do this. So, there are 4 states, 0 0 0 1 1 0 and 1 1. These are the 4 states here, 0 0 0 1 1 0 and 1 1. Let us say you start with those circles, then you go and look at on input 0, where do you go? So, you go to 0 0 itself. So, you draw an arc on 0, go to 0 0 itself, then 0 0 on a 1 goes to 1 0 state. So, 0 0 on a 1 goes to 1 0 state. So, you draw this arc and this arc by looking at just the 0 0 state. So, if I look at each one of these things, these are all giving me states and these are all giving me the inputs on which I have to make a transition, and these 2 columns will tell me to which circle or to which state I should be going. So, let us look at this row for instance. What this row says is, in the state 0 1, if you get 1 as an input, you should go to state 1 1. So, in the state 0 1, if you get 1 as an input, you go to the state 1 1. So, there are 4 different states and there are 2 transitions possible from each state. The transition using a 0 and transition using a 1, you will see that there are 8 arcs here. So, on all the input combinations, you go to one state or the other. This is the state machine that describes the circuit that is given earlier. So, this is a fairly straightforward and simple example. It was easy to get different equations and so on. So, in the real world, the state machines are not just 2 bits, it gets a lot more complicated, and if you have to analyze a circuit, you have to do this process of getting all the equations, finding out what the flip flops are, and based on the flip flops you have to derive the next state. So, let us move on to the next part or the different setup with the state machines, namely called the sequential logic synthesis. So, what we did so far is sequential logic analysis. Given a circuit, what it does. Now, the question is, given a problem, how do you design a circuit? This is something that is very common. So, the problem is specified to you in English and you are supposed to derive a circuit for it. So, this is called the synthesis problem, and the steps are actually straightforward, but it is the inverse process of analysis that we did earlier. So, in analysis you end up with a state machine, in synthesis you start with a state diagram. So, in the analysis you ended with a state diagram, in the synthesis you start with a state diagram. You construct the state diagram based on the English description that is given to you. Once you have the state diagram, you go and choose a set of state variables and assign combinations to them. So, we will see an example in a little while, this sentence will make sense. Then whenever you are told to construct a circuit, if you are going to synthesize a state machine, you should also be given constraints on what flip flops you can use. So, use the flip flops excitation table and derive the transitions and get the Boolean equations for it and draw the logic diagram. So, these are 5 different steps, but we will see them one after the other in a little while. So, this slide is there so that you can go back and look at the steps and see how to do it for a problem by yourself. So, before we go into the actual problem, we need to know what an excitation table is. So, an excitation table in some sense is the inverse of the analysis or the characteristic table. So, in an excitation table what you get is, if you are given Q and Q star, you are asked to guess what the input of the flip flop must have been. So, for instance, if I tell you that the present state of a flip flop is 0 and the next state is 0, and if I tell you that it is a D flip flop, then the question is what should have been at the input so that you get 0 in the next state. So, for Q star, for a D flip flop, so the previous state is 0, the current state is 0 also, which means you should have put D at the 0 input in the previous state so that the flip flops output will be a 0. So, this is called the characteristic, the excitation table. So, let us look at this row. If the current state is 0 and the next state is 1, I should place 1 at the end of the current cycle so that the next state will register a 1. So, that is this value here. Similarly, so since D is just delay flip flop, or what you have to do is whatever is present in the input will come as the next state. So, you can just copy the next state, that should be the input. So, that is one way to look at D flip flop. T flip flop on the other hand is interesting. So, 0 to 0 means you are not toggling, so T should have been 0. 0 to 1 means you are toggling, which means T should have been 1. 1 to 0 means you are toggling, so T should have been 1 to toggle. 1 to 1 means you stay at the same place, so it is 0. So, if I give you current state and next state, you are in the excitation table, you are actually writing down what should have been the value of the inputs to the flip flop so that the flip flop will go to the corresponding next state. JK flip flop is slightly more involved. If I give 0 0 as input, so either what this essentially means is, remember J is equivalent to set and K is equivalent to reset. So, definitely you should not be setting the flip flop, because if the current state is 0 and if J is 1, then this might actually go and change 0 to 1. So, you do not want that. So, you want J input to be 0 and K input can be 0 or 1. The reason is, if K input is 0, you are going to keep the old value itself, right. So, this is 0 0. So, if I want to go from 0 to 0, if I put JK inputs as 0 0, it will keep the same state, or if I put a 1, K is equivalent to reset. So, it is okay to go and reset a flip flop which is already at 0 to be at 0 itself. So, equivalently JK is 0x. So, J should be 0 and K is a do not care, whether K is 0 or 1, the flip flop will go to 0 itself. So, if I want to go from 0 to 1, you want to set the flip flop and reset should be, reset is this K flip flop, K input is a do not care. So, let us see how this works. If J is 1 and K is 0, then that is equivalent to just saying set. So, Q will go to 1. If J is 1 and K is 1, that is equivalent to saying toggle the flip flop. So, when you toggle from 0, you go to 1. So, that is equivalent to 1x. Similarly, going from 1 to 0 requires a x1 and 1 to 1 requires a x0. So, you can forget these two columns in the middle, Q, Q star, J, K, the excitation table is this table without this J and K columns in the middle. So that is the excitation table for a JK flip flop. So let us take a small example. Let us design a 2-bit binary counter using D flip flops. The state diagram is very simple here. So 0 0, in the next clock cycle it should go to 1, in the next clock cycle it should go to 1 0, in the next clock cycle it should go to 1 1, and finally it should go to 0 0. So there is no input here, and the transition means on every clock pulse you go to the next one. Let us see how to go about doing this. So let us look at how to use this information and derive a circuit. So we have the present state Q1 and Q0, and we have the next state Q1 star and Q0 star. So from 0 0 you want to go to 0 1, from 0 1 you want to go to 1 0, from 1 0 you want to go to 1 1, and from 1 1 you want to go to 0 0. Now we have to do the inverse process or using the excitation table. If I want to go from 0 to 0 for this flip flop Q1, then I should have placed D1 at the input. So that is what the excitation table gives us, right. Excitation table for D flip flop would tell us if I want to go from 0 to 0 I should place a 0, if I want to go from 0 to 1 I should place a 1. So let us look at this row. This one is suggesting that if this Q1 flip flop should go from Q0 to 1, which means you should place 1 at the input so that it can go from 0 to 1. And for Q0 it says it should go from 1 to 0, and if you want to go from 1 to 0, then D0 must be 0. So you can derive this and this using the 4 columns here. So once you get these 4 entries here, so remember this actually happens in combination, right. So Q1 Q0 is going from 0 0 to 0 1, it would go from 0 0 to 0 1 if you place 0 in D1 input and 1 at D0 input. Similarly Q1 Q0 will go from 1 1 to 0 0 if you place D1 at 0 and D0 at 0. So that is the meaning of this table. Once you have D1 and D0, you can forget this these 2 columns about the next state, because we want the relationship between present state and the flip flop inputs. Automatically flip flop inputs will dictate what the next state is. So you look at the 4 combinations in terms of Q1 Q0, and you look at D1, you get a corner map for it, D0 get a corner map for it. So the corner map entries are shown here and the groupings are also shown here. So it looks like D0 is Q0 complement and D1 is Q1 XOR Q0. So that is derived from these 2 vectors here. Once you have these 2 vectors, then now we are ready to go and do a circuit. We know how to do combinational circuits, right. So we will go and do a combinational circuit. So I will put the circuit here. So there is a flip flop, there are 2 flip flops Q0 and Q1, and the D0 of Q0 flip flop should be Q0 complement, and the D1 of Q1 flip flop should be Q0 XOR Q1. So that is what you have here. And if your flip flops Q and Q bar can both be tapped, then you can connect this directly here. If Q bar cannot be tapped, then you need to take this, put an inverter, and that will give you Q0 bar. And in this circuit Q0 and Q1 are directly going to the external world. So you can see that now this is resembling the canonical circuit, except that, so you have a state register, you have the input forming logic, there is no output forming logic, it is just the wire. So it is resembling the canonical circuit, except that you do not have the output forming logic, and the input forming logic on this line is either the line itself or it should be an inverter. So the combination is the input forming logic and the combination for this is the output forming logic. So what we did is something very simple. We started with analysis and now what we did is synthesis. So given a design problem, you draw the state machine for it. Once you draw the state machine, you know the state machine has these labels. You put the present state and next state, use the current whatever flip flop you have, derive the inputs, the D inputs in this case, and you take the D inputs and then you do the corner map, you get this. So what I suggest is you try and do the same thing with T flip flop. So do the same counter with a T flip flop. So the only thing that will change is this flip flop inputs T1 and T0, you should look at the excitation table for the T flip flop. See, I will suggest that as a homework, and so this brings me to the end of this module. So in the next module what we will do is we will look at the state machines in a lot more gory detail. So this is just a sample for state machines. In the next few videos you will see that the state machines are discussed in a lot more detail and in a lot more rigor, but do this little homework before you move to the next video. Thank you, and I will see you soon.